Alright, this is 2018 number 2. Start with a reaction, all gases here. And we start a little particle deal. So let's see, investigates nitrogen oxides. One of the reactions in the investigation requires equimolar of these two, which the student produces by using the reaction. Alright, so it's equimolar. Particle level representation of the mixture in the flask after the reaction. In the box below on the left, draw the particle level representation of the reactant mixtures of nitrogen monoxide and oxygen. Alright, so I'm taking the first thing I'm doing, I'm going to take the balanced equation here. I'm going to count up how many products I have on the in the final box. So I've got 1, 2, 3, 4 nitrogen dioxide particles at the end of this. I started with 0. I've got 4 of them at the end. And so we've got to figure out what else we've got. So at the end of the reaction, I've got 4 of these nitrogen monoxides still. Good. I've got 0 of these oxygens at the end, which means oxygen had to have run out. So oxygen was my limiting reactant. So I have excess of the nitrogen monoxide. If I produce 4 of these, then how many oxygens did I need to produce 4 of these? One of these would produce 2, and so I had to start with 2 oxygens on the reactant side. And how many nitrogen monoxides does that mean reacted with those 2 oxygens? For every one of these, 2 of these reacted. So if I had 2 of these, 4 of them reacted. I had 4 left over at the end, and 4 of them reacted, which means I started with 8 nitrogen monoxides at the beginning. And so that's kind of how I set that up. I just looked at the initials and the final values of the particles in that beaker, or whatever, the flask or whatever it was. And so I need to show the reactants. The initials were 8 of the nitrogen monoxides, 2 of the oxygens. There were no nitrogen dioxides. And so if I draw it up really quick in the box, little sleight of hand there, that's what mine looks like. 8 of the nitrogen monoxides, 2 of the oxygens. Yeah, you can mix them around however you want to mix them around. It was easier for me to count them this way if I separated those 2. But that's part A. That's it on part A, is drawing up those things. But you've got to look at the stoichiometry, figure out the limiting reactant, figure out that limiting reactant is going to determine how much of the other reactant you started with. It's also going to determine how much product you get at the end of that thing. There's a couple points in that. One for drawing the right types of reactants, and the other point on that thing is for putting the correct numbers of them. So that's part A. Then we get to part B. It says the student reads in a reference text that nitrogen monoxide and nitrogen dioxide will react to represent by the equation below. The student begins with equimolar of those 2 in a rigid vessel. Calculate the equilibrium constant for the reaction. So they give us delta H, delta S, delta G. If we have a delta G, we can calculate a K. And so that's what we're doing here on B. So on B, we know delta G naught equals negative ratlink RT natural log of that K value. And we're just plugging in numbers that we know. We know that delta G is 0.87. That's kilojoules. So important that that number they gave us is kilojoules per mole. That's going to equal negative. We're using our energy R. Our energy R is 8.315 joules. That's 8.315 joules per mole times Kelvin. We need kilojoules, so we're going to do negative 8.315 times 10 to the negative third. That will give us kilojoules per mole times Kelvin times the temperature. It tells us the temperature here. If they give us, that's what that naught symbol means, those standard conditions. So it's 298 Kelvin times the natural log of K. And so when I take 0.87 divided by those other 2, I get a negative 0.35. Don't forget your negative sign here. Negative 0.35 is equal to the natural log of K. And my big K there equals 0.704. No unit on big K, but we can calculate big K. Even though there's no acid-base equilibrium, that's an equilibrium constant, you should be comfortable converting from delta G to K. That's B1. Then B2 says if both the pressure of nitrogen monoxide and the pressure of nitrogen dioxide in the vessel are initially at 1, will the pressure, the final pressure of the product, be equal to 1? Because this is a 1-to-1 ratio, here's the conceptual idea. They didn't want you to actually calculate it, they just want you to do this conceptually. If I have 1 mole of this and 1 mole of that, that means they're both going to react fully with each other to form 1 of this if our K is big, right? Our equilibrium constant is big. If it has to be big in order to fully go to products. Because the K is less than 1, it's not very big, then it is not going to be equal to 1 atmosphere. And so what I wrote is the pressure of N2O3 will not be equal to 1 atmosphere. Answer the question, because the K value is less than 1 and therefore the reaction will not go to completion. I might even put reactants are favored. Not only does it not go to completion, but products aren't even favored in that reaction. So that's what I put. That's the idea conceptually. Could you, in theory, set up a rice table and solve for K? Here's the short version without a rice table. And if you guys want me to do this, I'll do this later. This is the pressure N2O3 over the pressure of the NO times the pressure of the NO2. And it ends up giving us X over 1 minus X squared equals 0.704. And you can actually calculate what X is there because we know the K value. And you could figure out what the pressure of N2O3 would be at equilibrium. But you don't need to. The answer, by the way, the pressure of N2O3 at equilibrium is 0.325 atmospheres. Just so if you get really excited and want to do it. Overachieving. Part C. Part C says the student hypothesizes that an increase in temperature will increase the amount of N2O3 in the equilibrium mixture. Indicate whether you agree, disagree with the hypothesis, and justify your answer. Here's the answer. Delta H is negative, which means negative. So the reaction, would the reaction be endo or exothermic? If it's negative, it means the delta H lies here, which means increasing the temperature would cause an equilibrium shift towards reactants. So the way you say is delta H is negative, so the reaction is exothermic, and an increase in temperature would cause equilibrium to shift toward more reactants. That's how you say it. What's the question on that, by the way? Indicate whether you agree, disagree with the hypothesis. Disagree. Don't forget to answer the question. I almost did there. Good. The last part of this is part D. There's actually an additional part E and F. This was a 10-point problem. The last 3 points are acid base. So we're only looking at 7 of the points here. The national average was 4.1 out of these, so you can kind of score yourself out of 7 and figure whether you got 40% of it right or not. If you got 40% of it, you are the national average. And so here's part D. Part D says N2O3 reacts with water to form nitrous acid, a compound involved in the production of acid rain, SOXes and NOXes. And so there is our reaction that they fed us. It gives us the skeletal structure of nitrous acid. It says complete the Lewis dot diagram in the box below, including any lone pairs of electrons. I start these guys. I talked about acids are hydrogen bonded to oxygen, at least oxyacids are bonded to whatever else. So we always have this structure at the beginning. This guy is always going to sit with that oxygen having those 2 lone pairs on it. It's worth counting up electrons for us. Each of those oxygens has 6 valence electrons, 5 more from nitrogen, 1 from hydrogen is 18 electrons, or 9 pairs of electrons is what I got. And so there's 1, 2, 3, 4, 5. You take care of terminal atoms next. 6, 7. If I put my 8th one here and my 9th one on nitrogen, my problem is my oxygen is satisfied, but my nitrogen is short on the octet if I add that other pair here. Good. And so I've got to take that pair of electrons that would normally be here, and I create a double bond to that nitrogen. That's the way that looks. So there's still 9 pairs, but that oxygen can't have 3 lone pairs on it because that would short nitrogen its octet of electrons. So there's our electron dot structure. Get a point for that. And then a fun quick hitter question. Based on your completed diagram above, identify the hybridization of the nitrogen atom in the HNO2 molecule. They want the hybridization here. How many bonding domains are there? It's atoms bonded to it plus lone electron pairs. So we've got 1, 2 atoms bonded to nitrogen. That lone pair of electrons makes 3 domains. And so we are sp2 hybridization is the answer to part 2 there. Add the exponents up to equal the domains. 1 from the S, 2 from the P's, 3 total domains, sp2 hybridization on that nitrogen. That's all I gave you on the 2018 number 2. Hopefully you got a bunch of those. We'll talk to you soon.